Hello, this is David Douglas. I'm the head of product marketing and applications development at Denton Vacuum. Today I'll be discussing some of the latest results from our tunable RF plasma ion source. We call it the Endeavor ion source, particularly how it relates to ion-assisted e-beam evaporation and some of the tunable film properties you can obtain as a result of using this source. This work was done in our applications lab, primarily by Mike Riley and Ravi Viswan, senior research scientists. Here's a brief outline of what I'll be discussing today. First, I'll give a brief introduction of Denton Vacuum for those of you who aren't familiar with us. Then I'll just discuss the ion-assisted e-beam evaporation, and then I'll move into a description of the RF plasma ion source. This is information that's been presented before. More interestingly, we'll move on to results and discussions of film properties and the tunability you can achieve with this ion source, and then a brief summary of what we discussed. So let's start with an introduction. Denton Vacuum has been around since the mid-1960s, founded by Richard Denton, an industry innovator and pioneer in the field of thin film deposition. We have over 5,000 systems installed worldwide across a wide variety of applications and markets, ranging from small SEM sample coders to large high-volume production tools, both cluster tools and inline systems. All of our systems are manufactured in the United States in our factory and application center in Morristown, New Jersey, and we have global sales and service offices around the world. One thing that's kind of unique for a company our size is we have a very strong emphasis on research and development of sources and controls. We have a lot of exciting new products based on our proprietary and patented deposition sources and ion sources, and one of those is what I'll be talking about in the balance of this talk. Before we do that, let's talk a little bit about ion-assisted e-beam evaporation. In ion-assisted deposition, we take a standard e-beam evaporation system and add an ion beam to it. In the standard e-beam evaporator, you can see in the cartoon here that we melt a material that we want to deposit onto a substrate here using an e-beam as the energy source, and we simultaneously apply an ion beam to the same substrates. These ions give energy to the evaporated atoms arriving at the substrate surface, which can enhance surface mobility, which can improve the density, stress, and grain structure of the deposited films. As you can see in the cartoon here, with no IAD, you can have voids, and then with ion-assisted deposition, you can densify this to a great deal and improve some of the properties. These higher density coatings result in greater moisture resistance, better mechanical durability, and lower optical scatter. The ion beam can also be used for pre-cleaning or etching of the substrate. However, there are some drawbacks of standard ion sources when used in this application. Ion sources with limited range of energy tunability can cause surface damage if used for pre-clean if they're a high-energy ion source. Most ion sources will either have a low ion flux with low ion energies or a high ion flux and high ion energies. This makes them kind of unsuitable for precise control during ion-assist deposition. They're really not practical for fluoride compounds or other easily dissociated molecules that you're trying to deposit because of the lack of higher ion flux coupled with lower ion energies. And this lack of tunability and independent control of both ion energy and ion current density prevents the use of a single ion source to be used for a variety of applications in one, including pre-clean, etch, and ion assist. Now let's talk about Denton's circular RF plasma ion source. Here's a simple schematic of the ion source. In this source, we inject working gas into a dielectric discharge chamber here, and we couple RF power into there inductively through this RF antenna, which is wrapped around the outside of the dielectric discharge chamber. And that provides the energy to create the plasma. And by varying that power of the RF, you can vary the plasma density. We have a neutral output grid here. It's grounded and conductive, so it's always neutral. And down here at the bottom of the source, we have a bias electrode, which we put a DC voltage on, positive voltage, and that pushes the ions out past the output grid. Since the grid is neutral, electrons are also free to go past there. And this actually, they're highly mobile, much more so than the ions. So you get a nice flux of electrons, and the beam tends to be self-neutralized then as a result. So you don't need any secondary filament or hollow cathode neutralizers to avoid charge buildup at your substrates. Another useful feature is the match network is integrated into the bottom of the source. It's not outside like many RF sources. That gives us freedom to place the source wherever is optimum for the architecture of the system. It works at a wide variety of gas pressures, from the standard IAD pressures of 10 to the minus 4 torr all the way up to the mid-millitorr range. Very interesting applications there for plasma-enhanced CVD, as well as potentially magnetron ion assist. We haven't explored that as much, but those are other applications on our roadmap. Well, we've done some characterization of this ion source looking at the ion beam itself. The ion beam profile, it comes out at a broad angular distribution of about plus or minus 40 degrees. We measured this with a Faraday cup array at about 30 centimeters working distance for a given power. We varied the voltage quite a bit and saw similar patterns. So the source is quite stable as a function of voltage. Here we demonstrate some of the tunability of ion energy. We put an impedance semi-ion detector directly over the ion source in the middle of the ion beam. And for a RF power of 2 kilowatts, we changed the extraction voltage from 0 to 150 volts. And you can see a very nice increase in the average ion energy as it goes from, with no volts, maybe 70 volts on average, all the way up to 220 or so when you have 150 volts applied to that extraction voltage. And of course, we can go higher as well, but we haven't characterized that yet. But you see very nice linear change in average ion energy as you adjust that grid extraction voltage. Now what happens if we turn our other knob, the RF power? Here we have the same setup. We use the same impedance semi-ion detector located directly above the extraction grid. Here we had no voltage on the DC bias electrode. So it's just what's coming out naturally without, from the RF power without any applied DC voltage. And you can see as you go up from 1400 to 1600 all the way up to 2000 watts, there is some slight shift in the ion energy distribution. But in general, they're very close. So you're not seeing much shift at all as you move out to higher powers. And you also see the signature of the electron flux, so you're getting that self-neutralized beam. So it's pretty stable in that 50 to 70 EV range as you go up in RF power from 1400 to 2000 watts. So then when we put them together, here we have a curve showing the tunability of the ion current density. We have an array of curves here for different powers, 500 watts all the way up to 2800 watts. And we're measuring the ion current density as a function of both the DC bias voltage and the power. And to get the low energy high current density then, you would work at the high power, all the way up to 2800 volts, and a low DC bias. And that's what gets you the high RF, high current density, but low ion energy. And of course, you can work in different regimes to tailor other film properties, and we'll be showing you some of those results shortly. So let's move on to the film results and discussion. The first thing we looked at was the refractive index for a number of materials. Here we're showing 3 different oxides. We're running the source in an ion assist, oxygen ion assist mode. For no IAD, we had the source off, so there's no RF power, no DC power here. And then we ran, for a fixed RF power of 2 kilowatts, we ran at various DC extraction voltages. Now, it's not so obvious with the aluminum oxide or the silicon dioxide, but with the hafnium oxide, you can actually see an intermediate step here at lower ion energies that you don't see the full refractive index until you get to the highest EV. So this is showing you some of the tunability. You can actually tailor that refractive index, for hafnium oxide at least, as a function of the ion source energy. The index change as a function of ion assist energy is probably due to the densification I mentioned earlier when we were talking about ion assisted deposition. Basically, if you have those voids, you have regions where there's an index of 1 mixed with index of 2 for the hafnium oxide, and when you average those there, they get lower. Interestingly, you can see the same effect in a moisture shift. Here we took 2 samples, same samples with no IAD here and with 300 EV, and we measured their transmission between 450 and 630, and then we measured them again after soaking both samples in water. Now, for a very dense film, putting them in water, since they're not water soluble, will have no impact on the optical properties. However, if you have voids in there and you replace those voids with water instead of air, you're basically raising the optical index on average of those films. And here you can see that pretty clearly here with the hafnium oxide. So with no ion assist, you see a pretty big gap here between the as deposited and after 24 hours. And there's about a 1% shift there, maybe a 5 nanometer shift in the center of the peak. And yet with using the 300 volt ion assist, you see a very small shift between the peaks, maybe 0.2% or 1 nanometer. So a much denser film probably, and a much more stable film in terms of moisture shift, which is much more useful to you. You don't want your optical filters to be shifting as a function of the humidity. That can be very detrimental to performance in various environments. Interestingly, when we looked at stress, we saw a reversal in the materials. The hafnium oxide showed very minimal change in the stress as a function of the ion source energy, ion source voltage. However, the aluminum oxide went down from about 30 megapascals tensile to 2 megapascals compressive, simply by increasing the ion energy from 0 to 100. The SiO2 showed a very strong response. This was compressive everywhere, but it varied between minus 100 all the way up to minus 500. And we barely saw any change in the refractive index, but we see a huge response in the stress tunability. Now this gives us some interesting knobs here. Here we show a 2-layer stress compensated coating test we ran. So we deposited a TiO2 layer with a relatively high stress. It had about 150 megapascals tensile stress. And then we also deposited a compressive layer of SiO2. So here in test 1, we actually vented and measured in between layers. And test 2, we actually just ran in one pump down. And in both, you see that this alternating highly tensile, highly compressive stress, you're able to get a net measured stress of very close to 0, 12 megapascals here and 28 here. This has some interesting ramifications for running on On flexible substrates, for example, one problem with flexible substrates with the stressy film is it tends to deform the substrate. But here, if we can actually tune it, then and stress compensate by the materials, then you can actually put this on a flexible substrate and get good optical properties from your multi-layer coatings while still maintaining a flat substrate. Finally, we can look at some uniformity and repeatability data to show the stability of the source. Here we ran titanium dioxide, a different material than I've showed before, except in that stress compensation stack. Here we did 5 consecutive runs with no changes in between and with the source running on the same conditions. And you can see the 5-run average of the refractive index is 2.445, and we measured a high of 2451 and a low of 2441. That is excellent repeatability for 5 consecutive runs, 0.3% on the optical constants. And the extinction coefficient was very low in all of them. There was some slight variability, but which may be attributable to the system cleaning up over a few runs running the same thing. One of the problems with demo systems is they're always doing different demos, so you might have some contamination in the first ones, but it's very small. So this looks like excellent run-to-run uniformity and repeatability here. And the average non-uniformity within each of the 8-inch substrate planets was 0.7%. So overall, very good results in the repeatability and the uniformity from this ion source. So in summary, we've shown that Denton's patented Endeavor plasma ion source can deliver high ion current density with low ion energy, independent ion energy control, and large area coverage over a wide range of RF powers. We demonstrated that the ion current density is controlled by RF power applied to the RF coil, and ion energy is controlled using the DC voltage applied to the internal bias electrode. This combination enables a high flux of ions with tunable ion energy. This ion beam tunability leads to tunable film properties, and we showed tunability in both moisture shift control and stress for single material thin films, as well as stress compensation for a 2-material stack. This ion beam tunability enables a single ion source to be used for pre-clean, etch, and ion-assisted deposition in typical e-beam applications. Thank you for your time, and I look forward to your questions. You can email me here.